Lesson 1, which will feature the uniform distribution. Unit 4 really starts the second half of our class. This is where we'll be switching from discrete probability functions into continuous probability functions, which will control what we're doing for the rest of the way. Remember, discrete meant that the random variables will be countable, so the values for x could be 0, 1, 2, 3, etc. Where continuous means an unlimited scale for x, so we can't really list out all the possible x's because there's infinitely many, and between any two, there's infinitely many more. X could be 1, it could be 2, it could be 1.5, it could be 1.012345. With an unlimited scale of possibilities for the random variable x, we don't really care so much anymore about specific data values, but instead we're going to care about ranges of data values. So instead of questions like what's the probability x equals 5, we'll be more interested in questions such as what's the probability x is between 5 and 8. When working with continuous distributions, it's critical to understand the idea of probability as an area. The only way to really calculate probabilities with a continuous distribution is to use what's known as a density curve. This is a graph that has an area underneath the curve equal to 1. The height of the ordered pairs in this graph will represent probabilities and must have a height of 0 or greater as a result. By calculating areas of smaller chunks of the graph, we're actually able to calculate probabilities. The easiest way to understand this concept is through the uniform distribution. While this isn't that important of a distribution to use, it's a really good distribution to teach us how probability as an area works, so we're prepared to use that for the bigger, more important concepts. Let's talk about what a uniform distribution is. It's a distribution where the probability of x remains consistent throughout the distribution. So you don't see it going up and down, but instead you see it flat throughout. This means that no particular area of x has a higher probability than any other area. Let's do an example that should help you to understand this. We're told that we have a uniform distribution from 3 to 13. We're going to draw an x-axis from 3 to 13. This represents the range of values that our random variable could be. Now, when you know it's a uniform distribution, you know it's going to have a rectangular shape. So we'll start off by drawing that. Now, what we don't know right away is the y-axis and specifically how tall this graph is. This y-axis represents the probability of x. Now, here's the way you can figure out this height right here. A uniform distribution is what we call a density curve. That means that the area of this rectangle equals 1. Well, remember, the area of a rectangle is base times height. We know the base is going from 3 to 13, which is 10 units long. 13 minus 3 equals 10. So we know the base equals 10, so 10 times the height equals 1, and if we divide both sides by 10, we get a height of 1/10. And that's how tall this graph is. Now, the trick, so you don't have to think that hard every time, is that the height will always be 1 divided by the base length, because the area will always be 1, so to calculate the height, you'll always just divide by whatever this base number is. And remember, we got that by doing 13 minus 3, the numbers from the base. Now, to calculate probabilities like we're asked to do over here, we just needed this picture, which we have now. What we're going to do is we're going to draw what x is greater than 10 looks like on the rectangle. Well, we're going to look at approximately 10 on the x-axis, which would be about here. We'll cut the rectangle at this point. And since it says greater, we want to shade to the right. Well, we can only make it to 13 because the distribution only goes that far. And what the concept of probability of an area says is whatever the area of this chunk of the graph is that corresponds to x is greater than 10, that's the probability of x is greater than 10. Well, this base is 3 units long, and the height is always going to be the same, which in this case is 1/10. So the probability is going to equal base times height, or 3 times 1/10, which gives us 0.3. And that's all we had to do. Now, in this next problem, we're told x is less than or equal to 8. Something important to understand is this less than or equal to versus just a regular less than. That meant a lot when we were doing discrete distributions, but in continuous it doesn't mean anything because there's not really a specific probability at an individual x value. We're only worried about ranges. So it doesn't really matter whether or not they put the line underneath. That won't affect any of the probability. So we're going to draw 8 on the x-axis, and this time they said less than. So we'll cut the rectangle at this point, and we'll find the area to the left of 8, which will only make it to 3, because the distribution stops at 3. So again, we're trying to find the area of this rectangle. Well, this one has a base of 5, and again a height of 1/10. Area equals base times height when we're talking about rectangles, so 5 times 1/10, or 0.5. Now I'm running out of room, so I'm going to redraw our picture real quick. No new calculations necessary, we're just redrawing it. And this time we're told 7 to 12. So I'm going to mark 7 and 12 on the graph. I'll cut the graph in both of those spots, and we're going to try to find this probability in the middle, or this area in the middle. Once again, the base of this smaller rectangle is 5, just like in that last problem we did, and we still have this consistent height of 1/10, so this is going to equal 5 times 1/10, which will once again be 0.5 as our final answer. Now here's a word problem that does the exact same concept. This heating and air conditioning service finds that the amount of time a repairman needs to fix a furnace is uniformly distributed between 1 and 5 hours. This tells me my setup. I'm going to draw a rectangle from 1 to 5. My base here is 4 units wide. And remember, my height's going to be 1 over the base, so my height will be 1/4. They're telling me more than 3.5, so we're going to go to 3.5 on the graph, and we're going to draw a rectangle to the right of it, since it's more than 3.5. If they said less, we would have gone to the left. The probability x is greater than 3.5 is going to be the base, which would be 5 minus 3.5, or 1.5, times the height, which is going to be 1/4. If you need it, this would be a good time to pull up your calculator and get back 0.375 as your area. And remember, the area is the probability. When you're dealing with a density curve that has an area of 1 underneath, whatever sub-area you get, so the area of the smaller shape corresponding to the interval we're interested in, is your probability, in this case 0.375. To conclude this lesson, I want to point out, while this lesson was obviously about the uniform distribution, it was much more importantly an introduction to how to handle continuous probability functions. Throughout the rest of the semester, we're going to solve these problems using what's called the density curve. This is a graph that has an area of 1 underneath. The sub-areas associated with ranges of values for your random variable can be used to calculate probabilities. So this lesson was all about how area can be used to calculate probability, which is a skill we're going to use throughout the rest of the semester. If you came away with anything else, write that down now, otherwise we'll see you in the next lesson.